Welcome back, math students. In this video, we are going to learn how to graph a rational function. So a rational function is a bit unique in the sense that it's got a denominator, and if you recall from the properties of rational functions, there's these things called asymptotes to contend with, and because of these asymptotes, the graph tends to look, well, a little bit different, meaning that it's actually not a continuous graph, unlike polynomials. So let's look first at the things that we either need to do or attributes of the rational function that we need to find in order to graph. So the first thing we have is we have this rational function, and we need to write the rational function and I'll title this R of x in lowest terms. In other words, we need to reduce this rational function, and to do that we'll have to factor the numerator, factor the denominator, and see if there are any common factors that we can possibly cancel out. The second thing we need to do is find the x and y intercepts. Along with that, we also would like to determine the behavior at each x-intercept. The third thing we need to find are any asymptotes. So we need to find any vertical, horizontal, or oblique asymptotes. For the fourth thing, we need to determine if the graph crosses the horizontal asymptote. So remember, a graph can cross a horizontal asymptote, but not a vertical asymptote. So it's possible that the graph does cross the horizontal. It may not cross the horizontal asymptote, and that's one thing we should determine. Number 5, the last thing, is to divide the graph into intervals. These intervals are based on the vertical asymptotes, and determine behavior near each asymptote. So for this problem, we are going to analyze the graph of the function r of x is equal to x minus 1 over x squared minus 4. We're going to follow the same 5 steps I just outlined, and as we go through each step, we're going to put what we know onto the graph to the right. So the first thing that we determined was that we need to reduce the function r of x into lowest terms. To do that, we should really factor the numerator and denominator if they can be factored. The numerator cannot be factored, but the denominator can be written as x minus 2 times the quantity x plus 2. Now, looking at our factors in the numerator and denominator, we see that it cannot, in fact, be reduced. Okay, so cannot be reduced. Now, this factored form will come in really handy when we start doing some of the other parts of, or some of the other attributes of the graph. The second thing we'll find are any x or y intercepts. So first let's find the y-intercept. So I'll take r of 0 is equal to 0 minus 1 over 0 squared minus 4. This produces 1/4 or 0.25. So right now we know there is an ordered pair of 0, 0.25. You'll notice that my graph to the right has actually a scale of 1/2. I did that to make it slightly easier to graph these smaller values. So our first point that we have on this graph is this y-intercept. The second point that we would like to find are any x-intercepts. So to do this, we will set y, or essentially our output r of x, equal to 0, and that would be equal to x minus 1 over x squared minus 4. Now to solve this, we would multiply both sides by the denominator of x minus x squared minus 4. And 0 times x squared minus 4 does in fact equal 0. So what we have now is 0 is equal to x minus 1. For future reference, you can just set the numerator equal to 0 to get the x-intercept. You don't need to go through that first process. So what we get then is x equal to 1. We have an ordered pair of 1 comma 0 then, and graphing that on our coordinate plane, we now have the ordered pair 1 comma 0. Now we need to determine the behavior near or at this x-intercept. So to do that, just like you would in a polynomial function, I will substitute the value of 1 into my function, except I will not put it into the factor that produced it. So the numerator is actually what produced this x-intercept. So I will substitute it into all x variables in the denominator. And I will simplify. So I will now have x minus 1 over negative 3, and then simplifying that a little bit further, or going a little bit further, it's negative 1/3 times the quantity x minus 1. So what this tells me is that this is actually decreasing through the ordered the x-intercept. So that tells me that we're going through the x-intercept, and we're going in a negative slope through that x-intercept. Okay, that's what that tells me right there. And I can go ahead and connect the y-intercept and the x-intercept in that negative fashion. Number 3, we're going to find the vertical and horizontal, or possibly oblique asymptotes. Now what's nice is because I've already gone ahead and factored the function r of x, I can see what the vertical asymptotes are without really having to do a lot of work. The vertical asymptotes are x is equal to 2 and x is equal to negative 2 based on the denominators here. So I'm going to go ahead and in blue put dashed lines, vertical dashed lines, where we have vertical asymptotes. Now remember, these vertical asymptotes represent a break in the graph. It's where we have an undefined x value, which means that we will have, in fact, 3 sections to our graph. We'll have one section here to the left, one in the middle, and one to the right, because the vertical asymptotes do, in fact, break the graph. So we'll have 3 sections, or you could call them branches to the graph, and it also means that this is a discontinuous graph. Now, to find the horizontal asymptote, there are some rules that you could use, but one way to find the horizontal asymptote in all situations is to divide the polynomial. So we could take x minus 1 divided by x squared minus 4. So does x squared minus 4 go into x minus 1? And the answer is no. So you would put a 0 in here, which means that y equals 0 is your horizontal asymptote. So by doing long division and dividing the polynomials, you can in fact get the horizontal asymptote. We're not interested in the remainder in this case because of the fact that that tends to go to 0. Again, go back and look at properties of rational functions to see how this is determined. So we know now that the horizontal asymptote is y is equal to 0, which is, by the way, the x-axis. For number 4, we need to determine if the graph crosses or possibly touches our horizontal asymptote, or if it doesn't do any of those things and doesn't cross or touch. So we actually already determined this because the horizontal asymptote is y is equal to 0, which by the way is the x-axis. Well, we determined that the x-axis has an intercept which is at 1, 0. So because the x-axis has the intercept, we know it either crosses or touches. Now, we know it's going to be doing one of those two things, crossing or possibly touching, because both of those represent x-intercepts. But here's the catch. We also know that because of this negative 1/3 as the slope near the x-intercept, we also know that it must cross. So that's why it must cross the x-intercept instead of just touching the x-intercept. So it crosses at the ordered pair of 1, 0. So we know that, and we again knew that based on the fact that the horizontal asymptote is the x-axis. Now what if, just let's say, what if the horizontal asymptote was not at the x-axis? So this is a hypothetical, and I'm going to erase this because this is not part of our work, but just let's pretend that the horizontal asymptote was y is equal to 2. Well, to do this, then you would set the function equal to 2. So 2 is equal to x minus 1 over x squared minus 4, and then you would go ahead and solve that to determine if, in fact, what the output would be for, or sorry, what the input would be based on that output of 2. And then you would find the intercept if it did intercept, and then from there you would go ahead and then find the behavior near it, probably based on number 5. So number 5 would be the where you would determine if it crosses or touches if your horizontal asymptote was not an x-intercept. Okay, so I'm going to go ahead and erase that work because, again, that was a hypothetical that really didn't pertain to this problem. So number 5, we're actually going to, and I'm going to scroll down just a hair, we're going to break up this graph into intervals and go ahead and determine what happens within the graph. So the first interval I have is negative infinity to the first vertical asymptote, which is -2. The second interval I have, or second section you might call it, is -2 to +2. And then finally the third is from 2 to infinity. So I need to determine what's happening within these, because all I really have now is 2 points in the middle section, and that's it. All right, so first thing I'm going to do is pick some value that's within this this chosen interval. So the first value I'm going to pick is -3. So I would like to find r of -3 to determine what the behavior is of the graph around near that that vertical asymptote, but to the left of the vertical asymptote, and I get -0.8 as an output. So this gives me an ordered pair of -3, -0.8. So -3, -0.8 is right about right here. So here's what that tells me, actually. That tells me a lot of information, just that one single ordered pair. Number 1, I know this is a horizontal asymptote, remember the x-axis, and I know that there is no x-intercept in this section of the graph. So I know that the graph is going to come along near this horizontal asymptote. It's going to decrease going through that ordered pair that I just found, going towards the vertical asymptote, and it's going to look like this. So that's going to be the shape of my graph in this section of the graph. So in the middle section, we already have these 2 ordered pairs, these 2 points that we already determined, the x and y intercept, but I'd like to find just one more, which would be r of 3/2, or 1.5. And when I find r of 3/2, so if I input this into my function, I get -2/7, which is approximately -0.29. So I'm going to go ahead and plot this ordered pair, so I know it's at 1.5, -0.29, so about right here on my coordinate plane. So again, here's what I know. I know to the right of the x-intercept, it's going to be going close to the vertical asymptote and then probably decreasing very sharply. And I know to the right, or left, sorry, of the x-intercept, to the left of the y-intercept, I know it's going to go towards the vertical asymptote and you're going to sharply increase it. So it's a decreasing function throughout, it's a decreasing branch to the graph throughout this entire section of this graph. Now finally, to the right of the last, or the second vertical asymptote, I'm going to choose +3 as my input, so r of +3, and this equals +0.4. Again, this tells me a lot of information. This tells me that the section under the curve is going to be above the x-axis because there are no x-intercepts in this section of the graph. So I know that I will be decreasing rapidly from the vertical asymptote. I will be going through that ordered pair I just found, which is 3, +0.4, and then I will be flattening out towards the horizontal asymptote as it goes to +infinity. So that's what I know based on the vertical asymptote, the horizontal asymptote, and the fact that there are no x-intercepts in that third section of the graph. I know there's a lot of information that goes into these graphs, but hopefully with these 5 attributes, or 5 things that you can do, you'll be able to successfully graph rational functions. Good luck.
This is a tricky one.